What's up, guys? Welcome back to linear algebra. All right. Let's see if we got any flashcards. We do. We got one. What is the forward phase of the algorithm for solving a linear system by Gauss-Jordan elimination? The forward phase. This is where you're going to be introducing zeros below the leading ones. Cool. Good. That's it for flashcards. So what did we learn about yesterday? Well, we're in matrix operations right now. So we learned that if you try to add or subtract two matrices that are not the same size, you're going to get an undefined answer. The answer will be undefined. Okay. Then we got into multiplying matrices. So how do you know if you can multiply matrices? How do you know if the product is defined? Well, you know the product is defined if the first matrix, the number of columns in the first matrix equals the number of rows in the second matrix, okay? So how are you going to multiply two matrices together? Well, basically, the resulting product, the resulting matrix is going to be, assuming that, like I said, the columns, the first is equal to the rows, the second. The resulting product matrix will be, size will be the rows of the first column by the columns of the second matrix. The rows of the first matrix by the columns of the second matrix, okay? And then how do you know what are the entries for each of those different entries? What are the numerical values for the entries of that resulting product matrix? Well, to find, say, the entry of entry 1, 1 in the resulting product matrix, well, you're gonna multiply row 1 of the first matrix times column 1 of the second matrix, and then you're going to add all the products together, place that into 1, 1. How about entry 2, 1? You're going to take row 2 of the first matrix times column 1 of the second matrix, multiply all the corresponding matrices, add up the products. There you go. Well, how about 1, 2? 1, 2, you're going to multiply row 1 from matrix 1 times column 2 of matrix 2, sum up all the products, place that into entry 2, 1. You get the pattern. And we also learned scalars are numerical values when we're referring to matrices. Scalars, scalar multiplication, okay? To multiply a matrix by a scalar, you're going to just take every entry and multiply it by that scalar. And to be considered this term, what is this term? Scalar multiple. Scalar multiple is basically a relationship between two or more matrices. Like their scalar multiples is defining a relationship in which you can get to from one matrix to the other matrix just by multiplying by a scalar. I think that's everything. Yep. Good. Good there. Good. Yep. Scalar multiple, is that what I referred to? Is that the term I said? Yeah. Okay. So that's everything. Now what I'm going to do is continue reading, and then I'll be back to recall in a bit. All right, guys, that was a huge day. I moved through a lot of this chapter or this unit because I wasn't really getting caught up on the details, wasn't getting tripped up, just kept moving. I got the general idea, kept moving, without being able to just visualize everything perfectly right away. But let's just see what we got. Row column rule. Row column rule? This is basically the abstraction of how to find is it just how to multiply matrices? No, it's how to find the entry. Yes, this is, okay. The row column rule is an abstraction of how to find basically any entry of a product matrix. Basically, you have the resulting matrix, say it's AB, capital AB in parentheses, and you want to know the entry at ij. Well, then that's going to equal lowercase a, basically entry A at row 1, row I, column 1, times B at row 1, column J, plus A sub I1 plus B, A sub I2 times B sub 2J plus dot 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 A sub IR plus A sub IR times B sub RJ. There's the row column rule. Okay, we got some background information. Before that, we talked about partitioning. What is partitioning? It's subdividing a matrix. You subdivide them into subdivisions. So you can create matrices within matrices by subdividing them by using basically lines called rules, vertical and horizontal rules, I believe. Practical application of partitioning is basically you're able to calculate or find any particular row or column of the product matrix without having to do the whole matrix multiplication. We learned a little bit of history about Eisenstein. It's like Einstein, but not. It's a German Eisenstein, who came up with matrix multiplication. It was later further developed by Cayley. Eisenstein was a student of Gauss. He came up with matrix multiplication as a way to simplify the process of substitution for linear systems. All right, what else we got? There's another term. What was this next section about? We covered a lot of sections today. Partitioning was a section. I think it's called linear combinations. Yeah, linear combinations. So another way, linear combinations is basically adding a bunch of matrices of the same size that are all multiplied by scalars known as coefficients. This is another way you can think about matrix multiplication. I think that's everything. Yeah, hell yeah, we got it all. Alright, guys. Yeah, what up? We are now on page 32. That's pretty cool. I mean, considering how long we've been doing this, it feels like days we weren't making any progress. Well, we've read Appendix A and B, and now on page 50 or 32. That's probably 50 pages in. So maybe 40. Yeah, that's pretty good. Stuff's dense, it's abstract, but I think we're learning some new stuff. We're getting a little smarter, a little better every day. So a few more pages of 1.3 and then we'll be into the problem set. So that's it for today. I'll talk to you guys later. See ya.